Hi everyone. In this video, I'll be talking about the electron-in-box diagram. In the previous video, you learned about principal quantum shells, subshells, and atomic orbitals. This diagram will help us better understand the distribution of electrons in the atomic orbitals. Before we go through how we can draw the electron-in-box diagram, we will have to learn how to label the atomic orbitals and how we can write down these electronic configurations. Recall that in the first principal quantum shell, we have an S subshell which has one atomic orbital. In the second principal quantum shell, we have a S subshell and a P subshell with 1 and 3 atomic orbitals. So, how do I label these atomic orbitals? I will be explaining this by going through two examples. First example would be carbon. A carbon atom has 6 electrons. Since electrons will always be filled up from the lowest energy level, electrons in carbon would first fill up the 1s orbital, which has the lowest energy level, followed by the 2s orbital, followed by the 2p orbital, and so on and so forth. So, since I have 6 electrons in carbon, 2 electrons will fill up the 1s orbital, which I will write as 1s2. 1 refers to the principal quantum shell, S refers to the S subshell, and 2 refers to the number of electrons. Now, we have 4 electrons remaining. The next 2 electrons will fill up the 2s subshell, which I will write as 2s2. The final 2 electrons will now fill up the 2p subshell, which I will write as 2p2. As you can see, we have accounted for all 6 electrons. Now, let us do a much harder example. We will begin by writing down the electronic configuration of manganese. In the manganese atom, there are 25 electrons. Again, let us look at the energy level diagram. Similarly, we will fill up from the lowest energy level. The first 2 electrons will fill up the 1s orbital, the next 2 electrons will fill up the 2s orbital, following which, the next 6 electrons will fill up the 2p orbital. At this point, we have accounted for 10 electrons and have 15 electrons left. We will continue this by filling up the next 2 electrons in the 3s orbital, followed by 6 in the 3p orbital, 2 in the 4s orbital, and lastly, the final 5 electrons will be in the 3d orbital. Now, we have accounted for all 25 electrons. Let me complete writing the electronic configuration of manganese. In terms of presenting your answer, we will write the electronic configuration as such. Note that when we write our answer, we write the 3d5 before the 4s2. This is because when we present electronic configurations, we present it in the order of increasing quantum shells. Now that we know how to write down the electron configuration for atoms, I will be going through how we can draw the electron-in-box diagram. There are 2 rules that we need to know for this. Firstly, Hund's rule of multiplicity. This rule states that when we fill subshells, we must fill up each subshell with 1 electron before we can fill it up with the second electron. For instance, if I have a 2p subshell, which has 3 orbitals, and I have 3 2p electrons, I must fill up each orbital with 1 electron. It will be wrong if I draw it in this manner. We are not allowed to pair up electrons when empty orbitals are still present within the same subshell. This is to minimize repulsion. The second rule would be the Pauli exclusion principle. This rule states that an orbital can hold a maximum of 2 electrons, and both these electrons will have opposite spins. As you would have seen from the drawing above, we represent electrons using a half arrow. When we draw an orbital with 2 electrons, we draw it such that both arrows are in opposite directions. This indicates that both electrons have different spins. Again, this is to minimize repulsion. Now, I am going to draw the electron-in-box diagram for the above 2 examples. Firstly, carbon. The first thing that we will do will be to draw out the empty atomic orbitals. Since a carbon atom has 10 electrons, we will only draw up to the 2p orbital. Now, we will fill up the 1s orbital with 2 electrons, 2s orbital with 2 electrons, and finally, the 2p orbitals with the last 2 electrons. This will be the electron-in-box diagram for the carbon atom. Similarly, for manganese, we will start by drawing the empty orbitals. For this, we draw up all the way to the 4s2 orbital. Similar to the previous example, we start by filling up from the 1s orbital, 1s2, 2s2, 2p6, 3s2, 3p6, 3d5. Notice that the 3d orbital has 5 electrons. Remember that we must fill up the empty orbitals with electrons before we can pair them. So, I will fill up each atomic orbital with 1 electron. Now finally, 4s2 for the final 2 electrons. You can label the number of electrons in each atomic orbital if you want to. This is the electron-in-box diagram for manganese. Do note that the 4s2 electrons are further away from the nucleus as compared to the 3d5 electrons, since they are in a higher principal quantum shell. However, we need to note that there are 2 exceptions to this method that we need to know. This is important as this is something that is commonly tested in the A levels. The 2 exceptions will be the electronic configuration of chromium and copper. So, for chromium, which has 24 electrons, when we fill up the orbitals, we will get the electronic configuration as follows: 1s2, 2s2, 2p6, 3s2, 3p6, 3d4, 4s2. However, in reality, it will exist as such. Notice that in the second electronic configuration that I wrote, we have a half-filled d subshell and 1 electron in the 4s orbital instead. Do note that we can truncate the writing of the electronic configurations by using noble gases to represent configurations. Another way that we can write this would be AR 3d5 4s1, where AR represents the electronic configuration of the noble gas argon. Now, for copper, which has 29 electrons, we'll get the following electronic configuration when we fill up the orbitals. However, again, in reality, it will exist as such. As you can see, this time, we have a fully filled d subshell and 1 electron in the 4s orbitals. Similarly, we can write it down as AR 3d10 4s1. Do you notice that in both cases, instead of 2 electrons in the 4s orbital, we have 1, and instead of 3d4 or 3d9, we have a half-filled d subshell 3d5 or a fully filled d subshell 3d10. So, what is the reason behind this? This is something that is commonly asked in the A levels, so do take note of the answer. The answer is as follows. Both these configurations have a symmetrical 3D cloud of electrons, which screens the outermost electron from the nucleus more effectively than any other configurations, which results in the lowest energy for the system. When something has the lowest energy level, this means that it is in its most stable state. Now finally, one last thing that is commonly tested in the A levels will be to write down the electronic configurations of cations and anions. So, how do we do this? For cations, we will remove the electrons starting from the outermost subshell, for example, copper. For simplicity, I will write its electronic configuration as AR 3d10 4s1. If we want to form the Cu plus cation, we will remove the outermost electron, which is the 4s1 electron, the electron that is the furthest away from the nucleus. Next, if we want the electronic configuration of the Cu2 plus ion, we will again remove an electron from the outermost subshell, which is now the 3d10 subshell. This gives us AR 3d9. Moving on, for anions, we add electrons starting from the orbitals of the lowest energy available. Let us use chlorine as an example. So the electronic configuration of Cl is 1s2, 2s2, 2p6, 3s2, 3p5. Again, let us use a noble gas to truncate the electronic configuration. If we want the electronic configuration of Cl-, we add 1 electron to the orbital of the lowest energy level available, which in this case is the 3p orbital. Hence, the configuration of Cl- will be Ne, which represents neon, 3s2, 3p6. In today's video, we learned about how to write electronic configurations, the electron-in-box diagram, and the 2 exceptions to this rule. If you find this video helpful, please support by giving a like and subscribe. In the next video, we will be learning about ionization energy.